The choice between a single large uninterrupted power supply or multiple units depends on several factors. Firstly, load capacity. Determine the total load requirement of the equipment to be protected. Secondly, redundancy. Multiple units provide redundancy, reducing the risk of downtime in case of a single uninterrupted power supply failure. Thirdly, space constraints. Single large units may require more floor space than multiple smaller units. Fourthly, cost. Multiple units may be more cost-effective than a single large unit. Electrical metallic tubing can act as a Faraday cage, reducing electromagnetic interference. Shielded or twisted pair cables can minimize electromagnetic interference. Harmonics can arise from the inverters in uninterrupted power supply units. Multiple units operating in parallel may amplify harmonic distortion. This can lead to increased voltage distortion and potential equipment problems. Inverters in different rooms may not have identical voltage and frequency outputs. Signal grounds and coax shields can create ground loops, causing current imbalances and potential noise problems. For critical loads requiring high redundancy and isolation, consider using multiple smaller uninterrupted power supply units. Install uninterrupted power supply units close to the load equipment to minimize cable length. Use shielded or twisted pair cables for power distribution. Ensure proper grounding and bonding to minimize ground loops. For parallel operation of multiple uninterrupted power supply units, consult the manufacturer's guidelines to address harmonic issues. Consider using an uninterrupted power supply distribution panel to provide isolation and fault protection for parallel uninterrupted power supply systems. When considering uninterrupted power supplies, it's important to understand the factors involved in selecting the right configuration, whether that's a single large unit or multiple smaller ones. Let's delve into the critical aspects to help make the best decision. Load capacity is paramount. Accurately determine the total power requirements of the equipment you intend to protect. This involves summing up the volt, ampere, or wattage of all connected devices. Selecting an appropriately sized uninterrupted power supply ensures that the load will be adequately supported during power outages. Redundancy is another key consideration. Multiple units offer a significant advantage in terms of redundancy. If one uninterrupted power supply fails, the others can continue to support the load, minimizing downtime. This is especially crucial for critical applications where even brief interruptions can have severe consequences. Space constraints can also play a significant role. Single large uninterrupted power supplies tend to require more floor space compared to multiple smaller units with the same total capacity. Assess the available space in the installation area to determine whether a single large unit is feasible or if multiple smaller units would be a better fit. Cost is always a factor. It's important to compare the total cost of ownership for both options. Multiple smaller units may initially seem more cost-effective, but factors such as maintenance, replacement costs, and energy efficiency should also be considered. Electrical metallic tubing, or EMT, serves as a protective conduit for electrical wiring. It also acts as a Faraday cage, which is a metallic enclosure that blocks electromagnetic fields. This shielding effect helps reduce electromagnetic interference, or EMI, which can disrupt sensitive electronic equipment. Shielded or twisted pair cables are specifically designed to minimize electromagnetic interference. The shielding provides a barrier against external noise, while the twisted pair configuration reduces signal radiation and susceptibility to interference. Harmonics are unwanted electrical frequencies that can distort the voltage and current waveforms in a power system. These harmonics are often generated by nonlinear loads such as electronic devices and uninterrupted power supplies. Multiple uninterrupted power supply units operating in parallel can potentially amplify harmonic distortion. This can lead to increased voltage distortion, overheating of equipment, and other power quality problems. Inverters in different rooms may not have perfectly matched voltage and frequency outputs. These discrepancies can cause circulating currents and other issues if the uninterrupted power supply units are interconnected. Signal grounds and coax shields can inadvertently create ground loops. A ground loop occurs when there are multiple paths to ground, resulting in unwanted current flow. These circulating currents can introduce noise and interference into the system, potentially disrupting sensitive equipment. When dealing with critical loads that demand high redundancy and isolation, consider employing multiple smaller uninterrupted power supply units. This approach offers enhanced protection against failures and minimizes the impact of disturbances. Installing uninterrupted power supply units close to the equipment they are intended to protect helps minimize cable length. Shorter cables reduce voltage drop and improve overall system performance. Always use shielded or twisted pair cables for power distribution to mitigate electromagnetic interference and ensure reliable power delivery. Proper grounding and bonding are essential for minimizing ground loops and ensuring electrical safety. Follow industry best practices and local electrical codes for grounding and bonding procedures. For the parallel operation of multiple uninterrupted power supply units, always consult the manufacturer's guidelines. These guidelines provide specific recommendations for addressing harmonic issues and ensuring proper system operation. Consider using an uninterrupted power supply distribution panel to provide isolation and fault protection for parallel uninterrupted power supply systems. This panel can help isolate faults and prevent them from propagating throughout the entire system. Uninterrupted power supplies play a crucial role in maintaining power continuity for critical equipment. Whether to use a single large unit or multiple smaller ones depends on a range of factors, from load requirements to redundancy needs. Properly implemented uninterrupted power supplies ensure that critical systems remain operational during power disruptions. When deciding between a single, large uninterrupted power supply and multiple smaller units, it is essential to consider load capacity, redundancy requirements, space limitations, and cost. Accurately assessing these factors will guide you toward the best solution. Load capacity is the total electrical power required by the equipment that the uninterrupted power supply will support. This is measured in volt amperes, or volt amps, or watts, and must be accurately determined to select the appropriate uninterrupted power supply size. Redundancy refers to the ability of a system to continue operating even if one or more of its components fail. Multiple uninterrupted power supply units offer redundancy, which can be crucial for critical applications where downtime is unacceptable. Space limitations can influence the choice between a single large unit and multiple smaller units. If space is restricted, multiple smaller units may be a more practical solution. The cost of each option should be carefully evaluated, including the initial purchase price, installation costs, and ongoing maintenance expenses. Electrical metallic tubing, commonly known as EMT, provides a protective enclosure for electrical wiring. Its metallic construction also acts as a Faraday cage, which helps to shield the enclosed conductors from electromagnetic interference. Using EMT can significantly reduce noise and improve the reliability of electrical systems. Shielded cables incorporate a conductive layer that surrounds the inner conductors, providing an effective barrier against electromagnetic interference. Twisted pair cables consist of two insulated conductors twisted together, which helps to reduce electromagnetic interference and crosstalk. Harmonics are unwanted electrical frequencies that can distort voltage and current waveforms. They are generated by nonlinear loads, such as electronic devices and uninterrupted power supplies. Multiple uninterrupted power supply units operating in parallel can exacerbate harmonic distortion, potentially leading to equipment damage and power quality problems. When uninterrupted power supply units are installed in different rooms, variations in voltage and frequency can occur. These differences can cause circulating currents and other issues that may affect the performance of the equipment. Ground loops occur when multiple paths to ground exist, creating unwanted current flow. These currents can introduce noise and interference into the system, potentially disrupting sensitive equipment. To minimize the impact of power disruptions, consider using multiple smaller uninterrupted power supply units for critical loads that require higher redundancy and isolation. Position uninterrupted power supply units as close as possible to the equipment they support to reduce cable length and improve system performance. Employ shielded or twisted pair cables for power distribution to minimize electromagnetic interference and ensure reliable power delivery. Ensure proper grounding and bonding practices to minimize ground loops and maintain electrical safety. When operating multiple uninterrupted power supply units in parallel, strictly adhere to the manufacturer's guidelines to address harmonic issues and ensure proper system operation. Consider using an uninterrupted power supply distribution panel to provide isolation and fault protection for parallel uninterrupted power supply systems. This panel can help isolate faults and prevent them from propagating throughout the system. Uninterrupted power supplies are essential for maintaining power continuity for critical equipment. Carefully consider the various factors discussed above to select the most appropriate uninterrupted power supply configuration for your specific needs. When determining the best approach for uninterrupted power supply deployment, whether it be a centralized single unit or distributed multiple units, several factors must be carefully weighed. A comprehensive evaluation encompassing load profiles, redundancy needs, spatial considerations, and budgetary constraints is paramount to ensure optimal power protection and operational efficiency. Let's explore these key aspects in detail. The load profile represents the aggregate power demand of the equipment the uninterrupted power supply is intended to support. Conducting a thorough assessment of the volt ampere or wattage requirements of all connected devices is crucial. This ensures that the chosen uninterrupted power supply solution can adequately handle the anticipated load, both under normal operating conditions and during power outages. Redundancy is a critical design consideration, especially for mission-critical applications where even brief interruptions can have significant consequences. Deploying multiple uninterrupted power supply units offers inherent redundancy, as the failure of one unit does not necessarily compromise the entire system. This redundancy ensures continuous power delivery, minimizing downtime and maximizing operational resilience. Spatial limitations can significantly influence the choice between a single large uninterrupted power supply unit and multiple smaller units. In environments where space is constrained, a distributed architecture with multiple smaller units may prove more practical than a single, bulky centralized unit. The available space must be carefully evaluated to determine the most feasible deployment strategy. Budgetary constraints invariably play a role in the decision-making process. A comprehensive cost analysis should be performed to compare the total cost of ownership for both single and multiple uninterrupted power supply unit configurations. This analysis should encompass initial acquisition costs, installation expenses, ongoing maintenance costs, and potential energy efficiency savings. Electrical metallic tubing offers robust physical protection for electrical conductors, safeguarding them from mechanical damage and environmental hazards. Furthermore, the metallic construction of electrical metallic tubing provides inherent shielding against electromagnetic interference, minimizing the risk of signal degradation and equipment malfunction. Shielded cables incorporate a conductive shield that surrounds the inner conductors, effectively blocking electromagnetic radiation and preventing external noise from interfering with the signal. Twisted pair cables, characterized by their twisted conductor geometry, offer superior immunity to electromagnetic interference and crosstalk, ensuring reliable signal transmission even in noisy environments. Harmonics are undesirable electrical frequencies that can distort voltage and current waveforms, leading to a variety of power quality problems. Nonlinear loads, such as electronic devices and uninterrupted power supplies, are primary contributors to harmonic distortion in the electrical systems. The proliferation of multiple uninterrupted power supply units operating in parallel can exacerbate harmonic distortion, potentially overloading electrical infrastructure and causing equipment damage. Discrepancies in voltage and frequency between geographically separated uninterrupted power supply units can lead to circulating currents and other power quality issues. These variations can arise due to differences in utility grid conditions or the inherent characteristics of the uninterrupted power supply inverters. Ground loops occur when multiple conductive paths to ground exist, creating closed circuits through which unwanted currents can flow. These circulating ground currents can introduce noise and interference into sensitive electronic equipment, compromising its performance and reliability. To mitigate the risk of power disruptions and ensure business continuity, critical loads should be powered by multiple smaller uninterrupted power supply units, providing redundancy and isolation. Strategically positioning uninterrupted power supply units close to the equipment they serve minimizes cable lengths, reducing voltage drop and improving overall system efficiency. Employing shielded or twisted pair cables for power distribution minimizes electromagnetic interference and ensures reliable power delivery to critical loads. Implementing proper grounding and bonding techniques is crucial for minimizing ground loops and ensuring electrical safety. Adhering to industry best practices and local electrical codes is essential for achieving a robust and reliable grounding system. When operating multiple uninterrupted power supply units in parallel, closely adhere to the manufacturer's guidelines for addressing harmonic issues and ensuring proper system coordination. Consider installing an uninterrupted power supply distribution panel to provide isolation and fault protection for parallel uninterrupted power supply systems, enhancing system resilience and safety. In conclusion, the selection of the appropriate uninterrupted power supply architecture depends on a careful evaluation of various factors, including load characteristics, redundancy requirements, spatial limitations, and budgetary constraints. By thoroughly considering these factors and implementing best practices for power distribution and grounding, organizations can ensure reliable power delivery to critical equipment and minimize the risk of costly downtime.